How many of the audience use the Siri on the iPhone 4S?
Other panel.
Is it good? Does it work for you?
No.
Oh, okay. Okay, well, after you attend this talk, you'll maybe know why it does it. Okay, Siri does stand for something. It's the speech interpretation and recognition interface. It's a speech-based user interface or experience, where the iPhone is the ideal platform because you don't have to type. You can use it on like when you're jogging or something like that, in the ideal case. And then it has something that we didn't have in the 90s. It has a cloud-based support, so you can put all your data that you want in the cloud. For example, you can ask Siri, where's the nearest restaurant? Then it will tell you. Then it has it's the result. It's not a small project. It's a result of the work of 7 universities, and including the Defense Department of the United States. Okay, what is speech recognition? Basically, it's just the translation of spoken words into text. Also known as ASR, or automatic speech recognition, or STT, but that's not used very often. Okay, this is my boss, Dr. Kai Fu Lee. When he was a PhD student in Carnegie Mellon, he made the breakthrough and made the world's first speaker-independent continuous speech recognizer. So I'll explain the terms later. CMU, of course, is one of the 7 universities in the Siri project. He created the Casper or Macintosh Plain Talk during the 1990s. If you use the Mac during the 1990s, you would have come across this in the system panel. You can turn it on. Then you can use speech to control your Mac. You can tell it to restart, shut down, and it will ask you, do you want to shut down? Yes, then it will blow. You see, so you can use it to do like print this document, save this document. So you can have a speech interface to any Mac application after you turn on the Casper speech recognition. So Siri probably still uses the techniques that he pioneered back in the 80s. So what is discrete speech versus continuous speech? So discrete speech is what before this breakthrough was you have to speak like this. I am going to the presentation. So you have to speak, you have to break your words. Otherwise the machine cannot know where is the breaks and try to recognize your entire speech as one word. So continuous speech, we try to detect where are the breaks, so you can just speak naturally. In fact, the more naturally you speak, the better it is for the system. Then speaker independent versus speaker independent. So speaker independent means in a wide audience who are not in the training set, they can use the system. So for example, in Siri, probably they use more than 10,000 speakers' contribution to the speech model, so that all the users in North America are covered. As long as you speak like the 10,000 users, the 10,000 training set contributors. Speaker dependent means it only works for you. Like you train the system, and after that, it only works for you. If your friend comes along and tries to use it, it will work very badly. This is an example of Siri not being able to work in England, for example. If you bring the North American model of iPhone to England, and you try to use it, then it will give you this kind of error. Until they make a model for England, then you can use it. This is okay because there's the database behind it. So necessarily, even if you can use it in England, the England model won't have the database for England. So if you make the query like, where's the nearest restaurant? It might not be able to tell you because it has not been built. So they build two databases at the same time. One is the speaker database and the information database. Okay, what is basic speech recognition? The most basic model you can build now, if you have a machine now, you can just take a sound sample, like a wave file, record it. That will be your template. Then the next moment, you record the same thing that you said. For example, you said template is hello. So now you make the speech hello, and you subtract your input S from the T, subtract T from S, and you get a 0. If you get a 0, that's the best case. That means you use the template and match with the template. So when you subtract, it's a 0. So that's the best result. So, but this is a very simple way, but it's not accurate, obviously, because when the next moment when you say the word hello, it will be very different. And when you subtract the values just as it is, you will have differences in position of the waveform. So this is just to understand how it works, but it's not done in the current world. So when you're training, you get the speaker to come in. You maybe give him an incentive by giving him a laptop bag, or maybe give him an iPad. So then he will read this script, which can be like an hour long of English phrases. So to train the system, so you have a training script which is already chosen to cover the sounds of English. So later I'll talk to you about the sounds of English. So from the training script, you extract the speech features. Then you build a model that all the other users will use from those who contribute their speech. So a training script can be like this. You make the user read sentences, like I was jogging on the track, the stock market is trending upwards. So from there you extract, because you know what he's going to say. So this can be used to build a model. So this is an example of how two users saying the same word can be very different. They're saying the word hamburger. So the waveform for the first speaker and the waveform for the second speaker, even though they say the same word, is very different. So how do we cope with such kind of data over the long period? So we have to use a technology. These are the sounds in the English language. So in the English language, there are 44 sounds. Though there are millions of words, they are all made up of these 44 sounds. And in speech recognition, we only need to use 39 of them. I don't know why we only need to use 39 of them. So the parts of speech are like, for example, as in and, as, after, as in and, and, land. So these are the parts of speech. We train the system on the parts of speech. And the representation in the machine will be like this. Like, for example, the word computer will be spelled computer, so that there's some kind of standard for the dictionary. Because the computer doesn't know how to read the word Python or whatever. So you got to specify the exact sound of it. Okay, then in the recognition stage, same thing, a microphone, preferably the same microphone. When you extract the speech features, and you go through something called a hidden Markov model, you get the best line of text. Then you pass this to the language model to try and understand what was spoken. The hidden Markov model, the definition, basically is something that allows you to guess a best guess of what happened that is hidden. Okay, I'll show you a diagram about it. Okay, this is the diagram that's on Wikipedia to explain the hidden Markov model. So you have this situation where you talk to your friend in another city, and he wants to know what is the weather in the city. So that's the hidden part. He cannot see where you are, So it doesn't know whether it was rainy or sunny. That's the hidden part. So, but you tell your friend, I went for a walk, or I went shopping, or I cleaned the house. So based on this, he knows the probabilities of what you did. And from there, he can make a good guess what was the weather in your city. So how does this relate to speech recognition? The bottom, the walk, the shop, and the clean is the recorded speech made by the user. So from there, we want to extract backwards and find out what was actually said. You see? So that's the hidden part, because you want to restore back what he said. So that the representation of that diagram in Python code will be like this. So when you train the model, you're training actually these probabilities. You're inserting these probabilities. So the more people train it, the more accurate this model will become. And you hope that it become so average that a user that was not in the training set can use the system and get good accuracy from it. Okay, these are the inside jokes of speech recognition. So, for example, you want to say Apple recognized speech, but actually it sounds like Apple wrecked a nice beach. So that's what we wrote on our T-shirts. That we threw litter on a nice beach, and because of the inability to distinguish the similar sounding words. So, like for example, like this famous song, I forgot what's the real name of it. Sewing machine. Yeah, sowing the seeds of love. Correct. Yeah, or that really boggles the mind, or that's an old wife's tale. So all these things will make the machine unable to distinguish, because we ourselves also sometimes mishear what other people say. So how do you clean up the signal that come in and avoid those problems in the previous slide? So you use this algorithm, this famous algorithm by Andrew Viterbi. This algorithm is used in your mobile phone. It's used in the deep space to communicate with the Mars rover, because over such a great distance, the signal is garbled. So using his algorithm, you can clean up the signal. So we use this algorithm in speech recognition to clean up the signal that's coming in, because there may be noise, the user might not pronounce correctly. So all that will make it difficult for the machine to understand the speech. So this is how it traverses through a sample of speech to find the correct path through it. You can get a visual idea of it, like for example, you pick out a sentence in your email, okay, and you remove all the spaces. So all the words are joined together. So how do you segment the word such that it's correct to become the correct sentence? Like for example, if the word that you're trying to segment is the result, but when they join together, it could become there also. So you have to make a best guess of what was spoken. Okay, so you end up with a language model. So language model just handles all the possibilities of saying something. Here you can say find an object, find another object, find the next object, or find the object. So this is language processing. So the Python libraries I use are enough to do the demo. So we have PyAudio to record the audio from the microphone. Then NumPy to do the FFT, which is a fast Fourier transform, to get the frequency of the speech, the dominant frequency, like what we hear. And then, of course, the HMM to train the speech model. Then natural language toolkit. And then finally, for output, use Python TTS, text-to-speech. This one, I'm forced to use the Microsoft Mary as the output sound. Because I trained it on a Windows platform, so I had to use Microsoft Mary. Okay, there are other speech recognition packages that already put together all those other libraries to make speech. Like for example, there's PySpeech, which uses Microsoft Speech SDK. So you have to go through all the training in order to make it accurate for yourself. Then there's Dragonfly, which is I think based on the Dragon model. So you have two engine choices in that case. Now this is an example of a PyAudio code to open the microphone and record speech from there. Okay, so quite straightforward. And then this is a NumPy fast Fourier transform to determine the frequency of a sound file. So in the end, you can multiply out and get the frequency in hertz. Then after that, you can train the model using the GHMM code. There you can see the Viterbi code, which is in part of this library. And then finally, you can output the text or give the answer via the TTS. So you don't have to read the screen, you just have to listen. Oh yeah, okay, the demo, there was I couldn't get the noise cancelling part to work. So I made a recorded demo because there were a lot of crashing and all that. And you see, I couldn't even set up my laptop to do the screen. So I was afraid it would have a big problem on today. So I made a recorded one. And also because that happened during my demo in 1996, there was I had made at least 100 demos to various people throughout the time we developed this software. But the last demo was to a minister. Thankfully, he's no longer a minister of Singapore. And he was there. And we said these words, 我们的, which means our. But the output came out as your mother in Chinese. But thankfully, he wasn't insulted. He still gave us the prize of the, yeah. After that, we made sure we hard-coded it. There will never come out this phrase. Yeah. Okay, so, this one is after the demo. So I'll give you the demo now. Okay. So this is, I'm running my demo in the command line on IPython. Hope you can hear it.
PyCon attack speech recognition demo.
Linda?
Yes.
Linda, I am hungry.
Who cares if you are hungry?
Linda, where is the nearest eating place?
What kind of food do you want to eat?
Mexican food.
The food court round the corner has a Mexican stall.
Linda, program my video recorder.
What channel?
Channel 10.
What date?
8 June 2012.
What time?
3 p.m.
3 p.m. Video recording set.
Linda, make a lunch appointment with Jane Tan.
What date?
25th July 2012.
What time?
1 p.m.
1 p.m. Lunch appointment with Jane Tan on July 25, 2012, 1 p.m. has been entered into your calendar.
Linda, send a message to Jane Tan.
What is the message?
Hi Jane, are you free for lunch on the 25th of July?
Your message reads, Hi Jane, are you free for lunch on the 25th of July?
Linda, what tech stocks should I buy?
I know what you should not buy. Facebook, hot hot hot.
Yeah, so that's the demo. So, any questions? Yes?
How does Linda know that Jane Tan is a person?
Oh, that one is I coded it in the language model. Yeah, it's a demo lah. It's not really a full language model, so that's why the response is so fast. I already hard-coded it as one of the names to recognize.
So in normal circumstances, does Jane Tan needs to be, for example, in my iPhone to know that it's a person?
Yeah, it means that in the real Siri system, when you entered the name Jane Tan, or when the system first started up in the background, it would have already made models for the name Jane Tan before you started to use it.
So if I say to Siri, send a message to Barack Obama, Siri wouldn't know who Barack Obama is.
He might know that, I don't know, because I didn't make the real Siri, but because Barack Obama is a famous person, it might be coded in the cloud already. Because if you've seen the demos of Siri on the cloud, in the web pages, people can ask questions like, how much can a woodchuck chuck in the wood? You know, a long sentence, and you can still get it. So that's quite amazing. It shows that they have improved the technology over the years. Yeah.
Yeah, I have a lot of questions about your demo. So I guess you demonstrated something quite sophisticated involving natural language understanding as well. Is that right?
It's actually simple, what do you call, dialogue management.
Yeah.
It's not really natural language understanding because it's just a simple demo. This is my hobby at the time. It's more like when it triggers by the video recording, then it will go into like video recording mode.
Yeah.
So at that point, it just understands the time and the date. Yeah.
Is that why there were no mistakes?
Yeah.
The language model is very constrained.
Yes, very constrained. Yeah.
And did you train it just on your voice?
Yes, I trained it 10 times on my voice.
Reading each of those prompts?
No. I read the training script.
Okay.
So the training script was used to generalize it for any other situation.
Okay.
Yeah.
Good.
Yeah.
And I guess the source code you're not making it available.
Oh no, cannot. I mean, if Apple was the Apple of 1997, maybe I would. But the Apple of today, I think I'll get a lawyer's letter.
How long is your code for that demo you gave?
Oh, not very long. But because a lot of the hard code is already written by those libraries,
Yeah.
so I just use them. Yeah.
Thank
Yeah. In the past, all those libraries actually represents a few scientists.
you. Yeah.
Because you have to go to them. There are no libraries in the world at that moment. So you have to, each person has to make all those libraries, the audio library, the language model, everything. Yeah. You're welcome. So what do you think of this sort of technology? Does it really meet your expectation? Like, do you treat it like a human, for example? Or do you know that it's a machine and know that it has limitations?
I think it's a neat technology, but I will always have a problem in public just talking to a device.
Yeah, that is a problem.
It just feels weird.
Yeah,
Talking to,
correct.
instead of talking to a human, at least if you're talking over the phone to another person, you're talking to a person. And when you talk to a device, it's weird.
Mm.
To you or weird? when you see
Well,
somebody doing it.
I feel weird, and when I see somebody else doing it, it doesn't look natural.
But how do you know you're not talking to a real one?
When he talks to Linda, I can tell.
And do you know in actual Siri, like how they are using Wolfram Alpha APIs and stuff like that?
Which one?
Siri uses Wolfram Alpha. That's what I.
Yeah.
You know that are they using it?
I know how to use it, but
Anything you've researched on those topics and
no.
Wolfram Alpha is the very good.
I heard it uses it, but I don't know how they use it. It maybe he gathered all the data for them. It may be because he gathered all the data for them.
Okay.
Yeah, because
Are
it's.
they doing it browsing itself, or they are just delegating it to Wolfram Alpha to give the engine answer?
I'm not aware of that because I'm not in Apple anymore. Yeah. Okay. Thank you very much.